Hello everyone, my name is Yujiro Ichikawa. I am from the Center for Environmental Science in Saitama, also known as CES. The title of this lecture is Basics of Canister GCMS Analysis. This is the presentation outline. First topic is about VOC sampling. In this topic, I will explain about canister and flow controller. And second, this is about canister GCMS measurement. This includes chromatography, mobile phase, VOC preconcentrator, GC column, and MS detector. Okay. Then I will start from first topic. The upper part in this picture is called flow controller, and the lower spherical container is called the canister. Atmospheric samples are drawn from the inlet of the flow controller, and sample goes through the flow controller and will accumulate in this canister. As you can see here, there are various sizes of canister. The largest is 15 liters and the smallest is 0.1 liter. You can choose the size depending on the purpose. Most commonly used size for atmospheric VOC sampling is 6 liter. This is about the interior wall of canister. The picture on the left side is canister with inert coated, and the right side is uncoated wall, just made of stainless steel. It has been experimentally confirmed that canister without inert coating on the interior wall do not stably store many VOC components. I don't think uncoated canister are not sold anymore, but be sure to use canister with inner coated canister. Next is about flow controller. Typically, the inlet section has a filter to remove particles and a rain guard to prevent raindrops. This filter is important because particles can absorb VOC, so it is important to cut them out and not to penetrate into the canister. And the red character part, the restrictor, is an important part that coarsely controls the flow rate, and I will explain about this restrictor in the next slide. And the vacuum gauge on the left upper side is to measure the internal pressure of the canister. This allows you to see how much the canister has contained the air sample. The diaphragm, this part, finally adjusts the flow rate. By changing the restrictor, the flow rate can be varied significantly. A table of correspondence between restrictor and flow rate is provided on the right side for reference, but this varies from manufacturer to manufacturer. As an example, I am showing you the flow controller restrictor from Antec Instruments. They have various restrictor code, and you can change the flow rate depending on how fast or slow you want to set up. That is all for the first topic, and I will move on to the second topic, and this part is about canister GCMS measurement. First of all, let me explain the history of chromatography. In 1906, Russian botanist Michael Twit, person on the picture, separated the plant pigments by pouring petroleum ether into a glass column with fine calcium carbonate to separate the plant extracts. This is known as the world first chromatographic experiment. And the word chromatography comes from two Greek words. Chroma, this means color, and graphy, this means writing. And I will explain the chromatographic terminology from Twit's experiment. The plant extract can obviously be paraphrased as sample. And petroleum ether can be described as mobile phase. And calcium carbonate can be paraphrased as stationary phase. And the glass tube can then be explained as column. And finally, the place to collect the color, in this case, can be said as detector. This is a schematic diagram of chromatographic measurement. Sample injection is made where the mobile phase is flowing and the components are separated by columns. Then they are detected by detector and the results are shown on the PC screen. In the chart, the vertical axis is intensity, which you could pick up quantitative information, and the horizontal axis is time, and the time is the time at which the peak of a component appears is called the retention time, and this is used as qualitative information. Okay then, let me explain about the mobile phase in detail. Gas chromatography versus liquid chromatography. If the mobile phase is gas, it is called gas chromatography or GC. And if the mobile phase is liquid, it is called liquid chromatography or LC. Analytic conditions required for GC analysis is that it needs to be gaseous or vaporizing compounds. In general, compounds that vaporize below about 300 Celsius degrees. And since GC applies temperature, analyte must be thermally stable. Molecule weight up to 1000 and non-polar to moderate polar compounds. As for the LC, analyte needs to be soluble in elute, or otherwise soluble in mobile phase. Molecular weight is in range of 50 to 100,000 and non-polar to highly polar compounds. The lower left figure summarizes the range of compounds that can be measured by GC and LC. Although the LC has a wider range of compounds that can be measured than GC, the greatest advantage of GC is that it has much better resolution than LC. From these features, you can find that GC and LC have different characteristics, and you need to use GC or LC according to the application and purpose. For the measurement of atmospheric VOC, GC is commonly used and has been adopted in measurement manuals in the US, Japan, and other countries. So this lecture will focus on GC. And next, I will explain about sample injection in detail. For canister measurement, canister autosampler and preconcentrator are commonly used. The area squared in the red flame is the canister autosampler and preconcentrator. The right side is the autosampler and the left side is the VOC preconcentrator in this picture. First, you mount the canister onto the autosampler. Then the VOC sample is sent to the connected VOC preconcentrator. To describe what kind of operations are conducted at the preconcentrator, the procedure steps conducted at the preconcentrator is described in the bottom part. The VOC preconcentrator accommodates 3 traps: trap 1, trap 2, and trap 3. As step 1, the VOC sample from the canister passes through cool trap 1 and 2. A brief explanation of this situation is that water remains in trap 1 and most of the VOC components will remain in trap 2. Water is something that you want to remove because it will cause a negative impact to GC analysis, such as bad peak separation and decreases the sensitivity. And step 2, trap 2, where the GC components are present, is heated and VOC components are sent to trap 3, which is cooled down to minus 160 degrees Celsius or sometimes lower. And for step 3, trap 3 is rapidly heated and sent to GC for analysis. And next, I will explain about the GC column. There are 2 types of GC columns: packed column and capillary column. Packed column are columns packed with particles such as carrier or solvent coated with stationary phase. And the capillary columns consist of a thinly stretched polyimide tube with a fused silica layer to which the stationary phase is applied. The table below summarizes the characteristics of a packed column and capillary column. Packed columns are made of glass or stainless steel, and capillary columns are made of fused silica or stainless. Capillary columns are more inert, and the inner diameter of capillary column is more narrower, and the length is longer for capillary column. The film thickness of the stationary phase is thinner for capillary column, and capillary column is thinner, so the sample load amount is smaller. And this theoretical plate number, this is related to with the column separation, and higher this number is, the separation will be better. And generally capillary column is better than packed column, and packed columns are still used for some specific analysis, but for the VOC measurement, capillary column is the one that is used most of the time. So I would like to explain more about capillary column in more details. The GC capillary column is further subdivided into three types: wall-coated open tubular (WCOT), support-coated open tubular (SCOT), porous layer open tubular (PLOT). WCOT consists of a layer of fused silica and liquid stationary phase inside polyimide coating tube. And SCOT is diatomaceous earth carrier coated with a fixed phase of fused silica. And the plot column will be those in which the porous layer or adsorbent solid are coated on fused silica. WCOT is versatile and have wide variety types of liquid stationary phase. On the other hand, SCOT and PLOT are mainly used for special applications. Factors affecting peak separation are the type and thickness of stationary phase, and column inner diameter, column length, carrier gas type, and linear velocity, and GC oven type. This table lists the pros and cons of carrier gas types. Nitrogen is cheap, safe gas, but the disadvantages are poor separation and the time consuming for one run. Hydrogen is cheap, separates well, and short runtime, but it is very explosive gas, so it got to be handled with great care. Last, helium, good separation, short runtime, but it is an expensive gas. In the measurement of VOC by canister, the preconcentrator system, which I explained earlier, uses helium to inject the sample into the GCMS. Therefore, helium is going to be the only option for this type of analysis. This is an example of measurement showing the difference in separation when the temperature of GC oven has changed. Sample is kerosene, and all the analytical condition is same, except for the temperature. From the chromatogram shown here, you can find that the faster rate of temperature, the peak is eluding earlier. It is necessary to set the temperature according to the degree of separation, measurement time, and etc. This section describes the types of stationary phase, other words, polarity. Stationary phase polarity can be classified as non-polar, intermediate polar, and polar. The chemical functional group that make up the general stationary phase are shown on the right side. Dimethyltrioxine is a typical non-polar functional group, and diphenyl, phenol, etc. Different types. All these different types of function are added to change and adjust stationary phase polarity. Different types of stationary phase columns are commercialized, and for the VOC measurement, non-polar to intermediate polar columns are often used. The main interactions between the column stationary phase and the compound are London dispersion forces, dipole forces, dipole-induced dipole forces, permanent dipole forces, and hydrogen bonding. In general, phenol, cyanopropyl, trifluoropropyl, etc. are introduced into columns with polydimethylsiloxane backbone, and which will result in various interactions between the compound and the stationary phase. And these different interactions between the stationary phase and compounds makes compound separation characteristic. This is an example of peak separation when you use a different stationary phase. All the analytical conditions are same except for the polarity of stationary phase. To show the difference easier, I have highlighted for decaying, naphthalene, dodecane in yellow. You can see that the pattern of peak separation differs. This comes from the difference of interactions between compounds and the stationary phase. This slide summarizes the effect of GC capillary column length, internal diameter, and film thickness on the measurement. Length is associated with column efficiency. The longer the column, the longer measurement time. When separating multiple components, for example 50 species, longer columns are typically used. And internal diameter is associated with column efficiency, and retention. Thinner improves separation. However, sample load amount is smaller. And internal diameter is strongly related to the film thickness and is represented by an index called phase ratio beta, which will be explained later. And next, film thickness. This is associated with retention and sample load amount. Thicker the retention is, stronger. However, the peak tends to become broader. Here is about the phase ratio beta. This is an index for column performance based on internal diameter and film thickness. The beta is calculated by dividing the radius by the film thickness multiplied by 2. For example, if you are using 30 meter length, 0.32 millimeter internal diameter, and 1.8 micrometer film thickness column, the phase ratio beta is calculated to be 44. This slide shows a difference in peaks for different phase ratio. You can tell that peak shapes or the retention is different. The table below summarizes the phase ratio as one indicator for analytical application and purpose. This is a reference table for phase ratio beta. The blue columns are the inner diameter size, and the yellow low are the film thickness size. And phase ratio is written in the middle of this table. The red squared part are the ones that are generally used for measuring atmospheric VOC. So when you are purchasing a new column, please refer to this information. This is a slide showing the relationships between film thickness and retention. When the analytical conditions are all the same except for the film thickness, you can see from this chart that the retention of the peak, especially the red squared peak, differs a lot in this case. So you can understand that film thickness can increase retention. Therefore, film thickness are more suitable for weakly retained components. However, thicker films tend to have broader peaks. So it is necessary to look at the balance between retention and the peak shape. Here is a table indicating the relationship between internal diameter and sample load amount. If the size of internal diameter is big, you can increase more sample loading. Generally, the first internal diameter to choose would be 0.25 or 0.32. Internal diameter of 0.1 or 0.18 or 0.53 are used for specific analysis. And finally, I will explain about the detector connected to GC. This slide highlights the types of detectors connected to the GC and their sensitivity. There are two types of MS detector method. SIM is more specific method for quantitative analysis, and SCAN is for both qualitative and quantitative analysis. Each of detectors lined up here has its own characteristics, but I cannot explain all the detectors listed here because of time limitation. So I will focus on MS detector, which is the main one used for VOC measurement. MS is connected as a detector after components are separated by GC column. The main composition of MS is ion source, mass analyzer, and detector. The inside of GC-MS needs to be kept in high vacuum condition. Because compounds to be detected are ionized at the ion source, but if air exists inside MS, ions will collide with air and become undetected. As shown in the figure below, high vacuum needs to be created so that compounds, or you can say ions, are detected without being affected by disturbances. The table here summarizes the commonly used ion sources: electron ionization, chemical ionization, field ionization, and photoionization are used for gas phase sample. Atmospheric pressure chemical ionization and electrospray ionization are the most common ion source for LCMS. This electron ionization, EI, is mostly used in GCMS. And chemical ionization, CI, is sometimes used, so I have included both description figure on this slide. EI procedure generates electrons at the filament. This filament part applied at most of the time 70 electron volt. Then the electrons collide with the compounds and they will be ionized. Since EI procedure is strong ionization method, it usually breaks the chemical bonds of the compound and forms many fragment ions. The CI method is similar to EI method, but uses reagent gas such as methane and isobutane. The CI procedure where the ionized reaction gas react with compound. Next slide is about mass analyzers. This table shows the main mass analyzers used in GCMS. Quadruple ion trap, time of flight, and magnetic sector is common types used in GCMS. Quadruple MS is commonly used for atmospheric VOC measurement. So I will explain only quadruple MS in this lecture. This is a schematic of quadruple. In quadruple MS, there are 4 cylindric rods. The opposite rods each other have same polarity, and the adjacent rod have opposite positive and negative voltage applied to them. Ions with mass to charge ratio in a certain range, which are resonance ion, can pass through the quadruple to reach the detector. And non-resonance ions, which are those not targeted for detection, cannot pass through quadruple and are excluded here. The ions that reach the detection unit are amplified by electron multiplier, and they are displayed on the PC screen as electrical signal, which can be confirmed as the peaks. Okay, this lecture provided an overview of VOC sampling and canister GCMS measurement methods. This is it for this basics of canister GCMS analysis online lecture, and the practical lecture will be given in my lab in October. So I'm looking forward to seeing you then. Okay, this is it. Thank you very much.